Hi, I'm Aidan. I'm a software engineer for AWS. I've been part of AWS for about 5 years and I've been interviewing for about half that time. I'm part of the EC2 Core platform organization based in Cape Town, South Africa, where I was born. And today I'm here to help you prepare for your system design interview.
Alright, so as you know, I'm Aidan and I'm going to be presenting the system design module today. So let's talk about what's going to be on our agenda for this module. We'll start off by defining system design, and then we'll talk about how you can approach the system design interview to set yourself up for success. Then I'll give you some tips which should help with the interview, impress your interviewer. Then some important areas to focus on and keep front of mind to make sure that you tick all the boxes that the interviewer might be looking for you to cover. And then at the end we'll go through an example. So what is system design? System design is the process of defining the components, modules, interfaces, and data for a system to satisfy specified requirements. Requirements which come from your customer, and your customer may be internal or external, and that's something we'll touch on in a moment. It's about the journey from high level to low level, thinking about things like scalability, availability, reliability, etc. Low level would mean your concrete implementation, your implementation details. High level does not mean high level of detail. In fact, it means almost the opposite. It means looking at the problem from a distance, from far away, so that you can take a holistic view of the entire system, including all of the components and their integrations. Two things to keep in mind. There isn't a single recipe for solving any particular system design problem. And it's also impossible to design a large system in an hour. These 2 points mean that you need to pick your battles. Because there is no silver bullet, and because of time constraints, you're going to need to collaborate with your interviewer to decide where your focus should go. And speaking about collaborating with your interviewer, the most important takeaway I think I can give you today is to tell you that it's not only about the answers you give, it's also about the questions you ask. So you need to figure out which parts of the system are the most important for you to be focusing your time on to solve the customer problem, and then use the time that you have to drill down into those bits and make sure you have them covered properly. Let's talk about actually tackling the system design interview. So it might seem obvious, but it's important to know that you can't solve a problem you don't understand. And understanding a problem means familiarizing yourself with the characteristics, the requirements, the users, the scope. And when you make sure you know all of those things, then you're probably going to solve the right problem in the right way, in the way that the interviewer is looking for. And you're going to be able to know that you're focusing your time on the right parts of the problem. So the best place to start is always to ask yourself, whose problem are you solving? When you know whose problem you're solving, then you know who your customer is. And when you know who your customer is, then you can work backwards from them. If you're at all familiar with the Amazon leadership principles, our number one LP is customer obsession. It always needs to be front of mind, and it allows you to build things that do the job that they're expected to do and end up delighting the customers. And that's how you keep customers happy, and you add more customers, and you earn trust. So yeah, make sure that you know who your customers are so that you can work backwards from them and solve the right problem. Now the next 2 points, the bottom 2 points, are about scope. It is easier to solve a problem when you don't have to think about a million different things, and you're able to scope down to what really matters. Scope, it's not only about which components you should be covering, but also what those components need to do. When you're talking about what is in scope and what is out of scope, you should think about not only the components, but also what they do and what they don't do. So to narrow down the scope, to figure out what is not in scope, you should do a couple things. That might mean that you need to ask the right questions, you sketch diagrams on the board, bounce ideas off of your interviewer. Do you know the constraints? What kind of inputs does your system need to handle? You have to get a sense for the scope of the problem before you can start exploring the space of possible solutions. And remember, there is no single right answer to any real-world problem. Everything is a trade-off. I have some tips that should help with your system design interview. My first tip would be to break the problem down into parts. Now, parts means different things to different people, and it means different things for different problems. So, for one person solving a problem, parts might mean the different components that make up the system. It might mean to a different person the various layers that make up the system. To someone else, it might be the different interfaces that your various customers use. You need to figure out what works best for you, but once you have, you will see how valuable it is to work with parts, because when you have parts, you can iterate through them. You can focus on each one by one and make sure that you cover all of the important bases related to that part. And as you're iterating through your parts, moving forward through the question, you're going to be learning new information. If you're not learning new information, then you're probably not asking the right questions. But as you learn new information, you need to make sure that if any of that information challenges assumptions that you made before, that you update your assumptions. It doesn't make much sense for you to stick to your guns about a decision you made earlier in the interview when you actually didn't have all of the information yet. If something challenges that, you need to ask yourself, do I need to update my assumptions? Do I actually need to change a design decision I made before because my calculation of the trade-offs is now very different? Gall's law says that a complex system that works is invariably found to have evolved from a simple system that works. The inverse proposition also appears to be true. A complex system designed from scratch never works and cannot be made to work. Like most laws in engineering, this is not a hard and fast fact. It's not a natural law or a physical law. It's more a rule of thumb. It pertains to an idea or concept which tends to be true most of the time. And this law basically means that if you want to build a complex system that works, build a simpler system first and then improve it over time. That is also a very important takeaway for you today. Finally, remember that there is no perfect solution. Every decision is a trade-off. Every decision is a trade-off. And you need to be able to explain each trade-off and convince the interviewer that this is the right trade-off to make. Why is this decision better than the alternatives? Firstly, what are the alternatives? Cool. Now we get to go over the important focus areas. So this list of focus areas is not comprehensive. The list of important areas in a system design interview is actually too long and would take way too much time, but the ones that we have here are probably the ones that we consider to be the most important, or the ones that will come up the most often in a system design interview. If you understand these areas correctly and you are able to make trade-offs in each of these areas to solve the problem in the best way and to cover all the things that the interviewer might be looking for, then that's going to be very good for you. So yeah, let's get started with it. So security is not listed here, but security is something that's sort of baked into all parts of a system from the ground up, usually, unless you're working on a security specific question, then you won't need to dive into security too much, and it's not often that questions like that come up. However, you do need to keep security front of mind when you're designing the other parts of your system. A scaling security flaw is not something that you want to have, and it also will help you make trade-off decisions about some of the other areas. So the first area for us to talk about is load. So this is all about how you scale when volume increases. So you usually get two kinds of scaling. You get horizontal and vertical scaling. Horizontal scaling is taking a single node and, not taking a single node. Horizontal scaling is increasing the number of similar nodes that you have that are serving traffic. Whereas vertical scaling is taking a single node and increasing the number of resources on that node. So a node could be your EC2 instance that's running your web server, or it could be your EC2 instance that's running your MySQL database. It doesn't really make a lot of sense to horizontally scale a database because there are a lot of complications that come with replicating data and keeping it consistent across multiple replicas. But it makes a lot of sense to vertically scale a server that's hosting a MySQL database, which is something that you can look up yourself and dive into. It's actually a very interesting topic. We talk here about thinking about what breaks when you increase the volume. So volume increase can mean different things. It can mean more data coming in, more data going out. It can mean more API calls, or it could mean an increased number of network messages, anything like that. But when these things go up, which parts of your system are going to break? How can you scale those systems to make sure that they don't break? And more importantly than fixing things after they break or knowing where they're going to break is monitoring those points so that you can step in and proactively resolve issues before they break, because when things break, then you're going to see customer or business impact. Monitoring involves metrics that are being emitted from your services, alarms that are built on top of those metrics to notify people when things are going wrong before they go very wrong, logs to help with debugging and troubleshooting. Correctness is about making sure that you solve the right problem in the right way, and you continue to solve the problem in the face of things going wrong. So you need to make sure that you satisfy the user requirements or the customer requirements or the business requirements. If you don't satisfy the requirements that have been presented to you, or you haven't made an effort to identify the requirements that you need to satisfy, then you could end up solving the wrong problem completely. It's not useful to build a perfect Facebook newsfeed if you've been tasked with designing a parking lot. You need to think about how your system can fail, and if there are any single points of failure. The list of ways a system can fail is never ending, but it's important to think about how it can and to plan for that. That's how you make a system more robust and more resilient and more available. Single points of failure have to do with when a lot of a particular kind of traffic all goes through a single node, and if that node goes down, then the whole system breaks. It might not even be a node. It could be maybe approvals need to go through a particular person in the finance department, and if they're sick, then nothing works. Or it could be if your master or primary database goes down, you lose all customer data because you haven't got it replicated anywhere. Or again, the list is very long, but you need to identify single points of failure and ask yourself, can these be removed? Is there a way that we can mitigate the risk if we can't actually fully remove them? Mitigating risk might be around making sure that data is redundant, saved somewhere else. If you have your entire web service running on a single rack in a data center and somebody goes and trips over the power cord, obviously that's going to be a major issue. So you can mitigate the risk by making sure that you're running on multiple servers and those servers are running on multiple racks, or even running in different data centers, or running in different availability zones or different regions. You get the idea. Integration is about how your components are connected and how they communicate with each other. So there's so many different ways that components can be connected. They could be passing messages directly to each other via some sort of common networking protocol. They could also be communicating synchronously or asynchronously. One component could be uploading messages to or not messages, but blobs of data to an S3 bucket, and then other parts of your system are then reading information from that authoritative source. So yeah, it's important to know how these things are connected and how they're communicating with each other, and what protocols that they're using to communicate as well, and what form those messages take. And then you need to think about what happens if a dependency breaks. Integration isn't actually just about how the components inside your system communicate with each other, but also how they communicate with things outside of your system. And those would be your external dependencies. If you're writing some piece of software that maybe aggregates a user's likes on Spotify, and you are querying you query the Spotify SDK to get that information. When Spotify goes down, you don't want your entire service to go down as well. It might make sense for you to cache the queries that you make periodically to Spotify, so that you can continue to make your recommendations and continue to aggregate the data even when Spotify is having a short outage. And then we come to state. So the first question, and most obvious question to ask, is where does the state of the system live? It could live on your servers in memory. It could live on a file system. It could run on a dedicated server that has a MySQL database on it. It could live in the cloud, either DynamoDB or RDS or in an S3 bucket. If it is stored in a server, what happens if that server dies? If it's a MySQL or PostgreSQL database that's running on a single server, and that server goes down, are you just going to lose all your customer data? Do you have it backed up somewhere? If you do, are you going to restore it? What is your system for restoring? Or are you going to have immediate failover to a replica that's kept up to date with periodic syncing? Or this is a deep rabbit hole to go down, but it's something that you should probably think about reading up on if you want to know more about it. And I would suggest that you do. If your state is distributed across components, how do you make sure that it's consistent? How do you make sure that no matter who's calling it or which node they're calling, they're going to get the same data? This brings us over to the CAP theorem. The CAP theorem talks about how we have to choose between consistency and availability when we experience a network partition. So the C stands for consistency, the A for availability, and P for partition tolerance. A network partition is a communications break within a distributed system. So that means a lost or temporarily delayed connection between two nodes. So when that's always going to happen in any distributed system, you cannot guarantee that for the rest of time you will not have a network partition occur. So when that does happen, you have to choose between consistency and availability. Consistency means that all callers see the same data at the same time, no matter which node they connect to. And availability means that any caller making a request for data gets a response, even if one or more nodes are down. But it doesn't come with a guarantee that the data is most up to date. So in your system, are you going to have CP or AP? CP means consistency in the face of a partition, or you're going to have availability in the face of a partition. This is something that you should probably also look up as well. It's again another rabbit hole and very important. You should think about what needs to be stored, what data needs to be persisted across time, and what are the characteristics of that storage. Characteristics refers to whether it is a relational database, or if it's NoSQL, or if it's key value, or if it's a network file system. There's so many characteristics that it can have, and even a relational database, it's like two different relational databases can have different characteristics. And if you think about what characteristics are important, then it will make it easier for you to decide what form your storage should take, or storage of your state should take. You should think about how your storage scales and how it fails. We've gone over this in some of the other sections, but the more you think about this, the more you can flesh out some other important characteristics of your system in general. Things like, scalability, availability, reliability. Okay, so time to run through an example. You own a large fleet of servers that runs a diverse set of workloads. Monitoring the health of these servers is critical to ensuring your customers have a good experience. Design a system to periodically run a suite of diagnostics to gather health data from these servers. Well, first things first, we need to make sure that we understand the question. And we can't fully understand the question if there is any ambiguity that we haven't dealt with. So if you want, you can pause the video now, and I will give you a second to see if you can come up with anything in this question that needs to be disambiguated. Alright, well, if large fleet was something that you thought might be ambiguous, then you're correct. If you thought there is ambiguity in diverse set of workloads, you would be correct as well. How many workloads? How diverse is diverse? If you thought periodically is ambiguous, again, correct. What does periodically mean? We haven't defined the period. And what exactly is a diagnostic? So I've highlighted the bits that might be ambiguous, and I'm sure that you did a good job identifying them as well. Regardless, in the system design interview, you want to make sure that you deal with that ambiguity right up front. You can't solve the problem if you don't understand the question. Do not make any assumptions. So, some questions you can ask the interviewer or yourself. What's a large fleet? The interviewer can tell you, in this case, it means thousands of servers. You say, what's a diagnostic? The interviewer says, a diagnostic in this case would be a small self-contained script. You might then ask, what does self-contained mean? Self-contained means that the script can be deployed without a complex dependency closure or any setup that needs to happen in the environment. It can run anywhere, and without having to be deployed with a bunch of other stuff. You can ask, what is periodic? In this case, it means hours. Some questions you can ask yourself, or you can try and work out by communicating with your interviewer. Who are our customers and what inputs, outputs do we want? Well, the customer here would be, I know in the question it mentions that, in the question we had on the previous slide, the full version of the question, it mentioned that we need to run these diagnostics to make sure that we keep our customers happy. But those would be our external customers. Those aren't actually our direct customers. Our direct customers would be the people who own the large fleet of servers, because you're designing a diagnostic suite to keep those servers healthy, which directly helps people who owns the servers and indirectly helps the people that your servers serve traffic to. And this might be your first pass at the problem. Something really simple. In fact, the simplest possible thing that might work. So you can see at the bottom, you've got your various servers, the servers that run the workloads. We haven't even decided where the diagnostic suite is going to live. And then we spoke earlier about how you should break your problem up into parts. Well, the parts that we've chosen for this is to separate into layers. And we're going to iterate through the layers, not in the order that we have here, but it's arbitrary, it doesn't really matter. We're going to focus on each of those layers before moving on to another one, and we'll see how we flesh out the idea and update our assumptions as we move along and add more information. The aggregation layer is responsible for running the diagnostic suite and, as the name suggests, aggregating the data that it gets from the diagnostic suite. We call it the aggregation layer here because it's just a name that makes sense. If you're solving a problem like this, it doesn't have to be aggregation layer. It's not always going to be aggregation layer. It just makes sense for this question. You could call it layer 1 if you wanted to, or some other descriptive name for a different problem. But here we're dealing with the actual diagnostics, so we need to flesh those out a bit and disambiguate those. So you might ask your interviewer, can you give me an example of a diagnostic, or maybe multiple examples? What does it do? Well, maybe the interviewer would tell you that when the diagnostic suite runs, it runs a number of diagnostics, and each of those diagnostics maybe make some checks on the server in terms of whether the resources are, well, whatever the values of the resources might be at any one time and how much of them are being used. So maybe how much disk usage is being taken up, what percentage of the CPU is being used up, how much RAM is being used up. There are all kinds of things that you might measure. Maybe it measures the size of the JVM heap or some other JVM metrics. It's bottomless what these diagnostics could do, but it's also important to know how much data the typical diagnostic returns, because that's how we get an idea of what's going to break if volume goes up. It also gives us an idea of how we need to build the system to be able to handle the load, well, the load that would be introduced by these diagnostics at the beginning. So, I mean, let's just say that it's just a couple kilobytes. So a typical diagnostic doesn't return a lot of information. How many diagnostics do we have right now? Hundreds. Basically the amount of data that needs to be transmitted when the entire suite runs would be a product of how much data a single diagnostic returns, the average amount, and then how many diagnostics we have in total. We might ask how often they run, and that would answer the question about the questions we had earlier about what does periodic mean. They might run serially, like all in a batch. They might run in parallel, or they might all be spread out over a couple of hours. These are also questions that it's important to get answered. And then, can new diagnostics get added? Yes, they can. And how often do they get added? Once or twice a month, so not that often. But now we just discovered a new customer for our system. A new customer are the people who are creating the diagnostics. They need a way to be able to create diagnostics and add them to the suite and have them run the same way all the other diagnostics run. So now that we've fleshed out what the diagnostics look like and what they do and how they behave, we can now get to making some serious design decisions. And the first one is, where do the diagnostics themselves live? Live means, where does the diagnostic code run? Where does it execute? Where is it stored? Well, we have two main options, I think. So the first one would be, we could deploy the diagnostics directly to the servers. So we have the servers that run the workloads, and then the diagnostics can be located on those servers as well. So each server has a full replication of the entire diagnostic suite. And then that means that the diagnostics are deployed to the server fleet in the same way that the workflow code is deployed to the server, so we can just leverage that deployment system. And then we can have the diagnostic processes push all of their results up to the aggregation layer, or up to the aggregation service, which is located in the aggregation layer, rather than have, well, we'll get to option 2 in a moment. The downside of this is that it's not very flexible. And by that we mean if we need to make a change to the diagnostics very rapidly, we might not be able to, because we have to deploy it with our other code. And if our workloads are busy running or being executed, something important is happening, we can't just go and take out servers and put new code onto them and then start them up again. That might have impact. So it's inflexible in that sense. And another problem is that in the future we might have resource contention. Because the diagnostic suite is running on the servers where the workloads are running, I mean, right now it's not much of an issue because we said that they just a typical diagnostic returns a couple kilobytes of data, but we have no idea right now how big those diagnostics might get, new ones that are created. Is there any limit? And does that mean that if we one day have thousands of diagnostics, or we have just a couple really big ones running in the suite, is that going to affect the ability for the standard workloads on the servers to do their job properly? Or is there going to be contention between the workloads and the diagnostics when they're trying to access CPU cycles and RAM? The alternative to deploying the diagnostics directly to the servers is to run them from some central workflow service. So this means that instead of deploying the diagnostics to each of the servers, we have a completely different set of servers, or maybe one server. You probably want more than one if you wanted to mitigate the risk of single point of failure. And you would deploy the diagnostics directly to that workflow service, and then that workflow service would remotely run diagnostics against the workload service, the main service. This sounds good in theory. It also helps with our deployment problem because we don't have to deploy the diagnostic code with the main code, but it does come with a security issue. The security issue is that allowing arbitrary code execution from remote servers is asking for trouble. Remote execution in general is something that you want to avoid unless it goes through very stringent authorization protocols. So for now, we can lean into a little bit of you ain't gonna need it and say that the easiest thing to do is to make use of the current deployment system that we already have and just deploy the diagnostic suite onto the servers, and then just have those diagnostic suites also push their code up to the aggregation service. Let's iterate over to the next layer. In this case, it's the storage layer. So the diagnostics are running on these servers that run the workloads, and they push their data up to the aggregation service, which does some cleaning, some wrangling, aggregating, obviously, and then it needs to store it somewhere. So what exactly are we going to store? What is the aggregation layer going to hand over to the storage layer to store? Makes sense that if we are measuring values as they change over time, that we would want to save them in a time series. If you're not familiar with a time series, jot it down and look it up after this video. And it's important to know what the output of the diagnostic is going to be as it goes into the aggregation layer, and then what it's going to be as it moves from the aggregation layer to the storage layer. Could be anything, right? But if we're keeping a time series, then on the y-axis we'd want to have some quantifiable value. So if we keep it super simple, we can make it an integer. And then how do we identify each server? The data that's coming in is just integers, and it might be for a particular kind of metric. Maybe it's percentage CPU used at any one time. as an integer, but how do we attach that value to a particular server? Because if things go wrong, or if there's something alarming about the diagnostic data, we need to attribute it to a particular server so we can take action on that server. So how can we do that? Well, we could answer that by just keeping the IPs fixed. So IPs are generally on a network how we identify nodes. If they're changing dynamically, then that's not going to be very useful unless we keep a table somewhere else that keeps track of all of the IPs for a particular MAC address or something, but that's probably too complicated. So if we just assume that the IP stay fixed and we state that outright, then we've shown that we have thought about this issue and we've come up with a solution for it. Another key decision to make is, do we need to keep history? We can probably ignore history for now until we find a need for it. The interviewer in the question hasn't really stated that there is any need to keep historical data, so keep it as simple as we possibly can. You ain't gonna need it, so let's go with just trying to keep it live. We also need to uniquely version our diagnostic results. So this answers the question, what data is stored and how is it stored? So we have integer values that are coming for particular diagnostics, and we have IP addresses to show that these values are for a diagnostic running on a particular server. But then we also need to attach a timestamp to it so we uniquely version it, because every time the diagnostic runs, it emits a new value, and for us to plot that as a time series, we would need a timestamp. So that's another piece of data that we would add. And then how are we going to store it? Well, if you ask the right questions, you'll work out that the system needs to support ad hoc queries. That means people generally need to be able to query the data as needed in interesting ways. And I'm sure you're all familiar with a very common language for querying data, and that's SQL. Or SQL, some of you might know it. So if we go with the simplest thing that allows us to store this data that we've described with a timestamp, uniquely versioned, with an IP address, and we also want to be able to make queries against it in a simple, straightforward way, we can use a single relational database. If you want to get into a discussion about whether it should be MySQL or PostgreSQL or something else, you can, but then you need to make sure that you understand the technological trade-offs intimately. Otherwise, you should consider it out of scope. And now we get to our third part, our third layer, the presentation layer. So we are generating this data, we are aggregating it, and then we're storing it. But it isn't useful to store data unless we're actually doing something with that data. Storing stuff takes money, time, resources, effort. So what is the use that we're trying to get out of this data, and how can we make it useful? So to present data means to show the data or to give the data. Give the data means to pass it, allow some other service to grab it and use it for its own purposes. And to show the data means to present it in a way that is generally easy for humans to read, analyze, and make sense of. So we've uncovered a few use cases. We want to be able to query the data, make ad hoc queries, or have other pieces of automation or other components query the data as well. Then we need a way to display it to the operators. All this diagnostic data that's getting spat out every couple of hours would be very useful in terms of measuring the health of your service. In general, you would want to show it using pretty graphs or in tables. And then on top of that, you would also want your
some of the services that are ingesting this data to detect if there are any issues so that it can light something up in red or page someone. Just let the operators know that something is wrong or is about to go wrong so that they can proactively deal with it. This is how you avoid flying blind. And now we've identified another customer. It's whoever is consuming the data that's being presented. So this customer might be the same as the people who own the servers that run the workloads, or it might be a completely separate ops team, or it might be leadership. So there's a good chance that there's overlap here, but it also might be a completely distinct customer. And now we've fleshed out our very simple design into something a little bit more complex. You can see we still have our fleet of servers at the bottom, and then inside each of those servers we have this little square, and this little square here represents the diagnostic suite that gets deployed onto each of the servers that are running the workloads. And those diagnostics run on these servers using the resources on these servers, and then they push their results up to the aggregation service, which aggregates and wrangles and cleans and filters or whatever you want it to do before dropping it into the relational database. This is how we signify databases when we're doing diagrams normally, so don't be confused by the symbol when you see it in the future. But the relational database represents basically the entire storage layer, and it's got a very simple schema. We have the IP of the host where the data came from, the diagnostic that ran, and the result, which could be an integer. We also said we wanted to uniquely identify with timestamps, so we can include that as well. And then the presentation layer is made up of the query service and the event service. You can see that's what the operators interact with. So the query service would be the interface for the operators to make ad hoc queries to the database. It might also be how other services make queries to the database. In some cases, your operators can interact with your database directly using SQL, but in this case it seems that we want everything to go through this query proxy. And then the event service is a service which automatically ingests streams of data from the database as they come in, and it monitors the data, and when it identifies that something is wrong or is about to go wrong, it lets the operators know either by sending an email or firing an alarm or paging someone. But yeah, this gives operators a head start in dealing with any issues which may come up from these servers picked up by the diagnostics. So we took our very simple 3-layer design and we fleshed it out a bit, and now we've got something closer to what we're going to have in the end, but it's still a rough skeleton. There's still many decisions to be made, and we're not at the end, but it's also not obvious exactly where we should go from here and how we should be spending the rest of the time in our interview. We've already dealt with a lot of the important characteristics, but the interviewer might still be looking for you to cover certain things, and the best way to find out what needs to be covered is to ask questions to find out what more requirements there might be that you haven't worked out. Spend more time thinking about the inputs and outputs, and asking questions like, do we need to know that our design is working correctly? So we have an event service in the previous slide which measures the diagnostic, which monitors the diagnostic data to see if the servers themselves are working. But on top of, separate from all of that, our system should need a way to make sure that data is getting from the diagnostic suites to the aggregation layer correctly, and that the aggregation layer is doing what it's supposed to do, and that it's saving stuff to the database, and that our query service is working the way it's expected as well. All of these components need to be integrated. If we update software, do they still all work? This is something that's often overlooked in the system design interviews, but making sure that you have good metrics, good monitoring, dashboarding, alarms, logging, canaries. These are all things that you could add to your system to make it more resilient, and to make sure that you are getting the data feed you need to make sure that your service is working as expected. Another thing you could cover is how your system gets deployed. It's made up of lots of components. Do they all deploy together? Is it a microservice architecture where they deploy independently? How do you make sure if they deploy independently that they are still able to integrate as expected? If you're not familiar with the concept of CI/CD or CI/CD, continuous integration, continuous deployment, then that's something that you should spend some time reading. It's an integral part of making sure that as you make changes to your system and update it, that it continues to work the way you need it to. How do we ensure that we're monitoring every host we have? Maybe it's imperative that every one of the servers that we had at the bottom layer are working all the time. If it is, then we need to know if one of them is not emitting data. It's one thing getting data that says that something is wrong with the host, and it's a different thing not getting the data at all. So how do we know if one of the hosts is not emitting data? Like the plug's been pulled on it and it's not on, and so the diagnostic suite is not there and it's not executing and it's not emitting anything. We might have a separate service which pings all of the servers behind the load balancer to make sure that they're healthy. Or maybe we expect a certain number of diagnostics to be emitted every hour. How do we automate this so that we don't have to have humans checking all the time? And then how do we distribute traffic? This is commonly answered by making use of a load balancer. A load balancer is a single entry point into a fleet of servers, and as the name suggests, it balances load across the servers. There are different rules and protocols for how it balances that load, and it's an interesting topic by itself and an important one as well. So if you want to spend some time looking up load balancing, then I would encourage that. This is also not a comprehensive list. There are so many other questions you can ask and so many other things you can explore. The only way to know where you should be putting your time is to collaborate with your interviewer. Here are some common mistakes to avoid in your system design interview. A very, very common mistake is that candidates like to spend a lot of time focusing on a particular technology rather than focusing on the design, the high-level design. Technology is, if you're looking at things from a high enough level, then the choice of technology is effectively an implementation detail. And often candidates will pick the technology that they're most familiar with. If you are going to pick one technology over another, it's a trade-off, and you need to explain why you're making this particular trade-off and why the technology you have chosen for this component is better than the alternatives. If you're not comfortable doing that, then I would suggest steering clear of technology decisions. For example, you almost never need to say that you would pick a language like Java and C++ over a language like Python or Ruby, or the other way around, unless part of the problem was that maybe it's an embedded system, in which case maybe an interpreted language like Python or Ruby is not performant enough. That's very seldom going to happen. Another example would be saying that you're going to use a messaging service or notification service to send messages between components serverlessly. And you can, instead of saying you're going to use Rabbit or Kafka or SNS or anything like that, you can just say you're using a messaging service that works in a particular high-level way. Another thing to do is to avoid rabbit holing. So rabbit holing is drilling deep into a specific part of the design, or drilling too deep, and you shouldn't really do that unless the interviewer explicitly asks for more details about a specific part. This could, if the interviewer isn't looking for a lot of detailed information in that particular area, then you're wasting time, and you're taking valuable time away from yourself, time that could be better spent on another more important focus area. Do not forget to discuss every trade-off decision, and remember, almost every decision is a trade-off. And do not forget to ask the right questions to solve the right problems. These last 2 points we kind of hammered home a few times in the session. I cannot stress enough how important they are. Anyway, if you enjoyed this module, then I'm very happy. I hope that it sets you up for success. Feel free to reach out to me outside of the Amazon network, or if you get a job inside of the Amazon network. And best of luck. Cheers.